All right, thank you very much. So I'd like to thank the organizers for inviting me and for setting up the winter school. So today I'll be talking about quantum error mitigation. So this is slightly different than the quantum error correction and intended more for the near term. So this consists of two lectures. The first lecture will look at noise channels, noisy gates, readout error mitigation and noise learning. And then in the second lecture, we'll look at probabilistic error cancellation, zero noise extrapolation, and coherent Pauli checks. Okay, so one of the key primitives of quantum computing is to measure an observable value, the expectation value of an observable. So for some given state rho here and an observable O, what we want to calculate is the expectation value, which is given by the trace of the observable with the state. Okay. And this has use, for example, in quantum chemistry. So we may be interested in the lowest energy state of some molecule. And what variational quantum eigensolvers do is they have some set of angles here denoted by theta. They form a state based on this, and then they compute the inner product with the Hadamard. To put this another way, is if you just take the trace on this side and then use the fact that you can rotate the terms, you get the trace of some Hamiltonian with this state. And for example, you can then express the Hamiltonian as a sum of Paulis and evaluate this trace for each of the Paulis and sum them up. Another example, for example, is the Ising model simulation. So you have time evolution of some one-dimensional transverse fields Ising model. So the Hamiltonian is just given by Pauli Z terms on neighboring pairs, plus a Pauli X term on each of the individual qubits with different coefficients. And then you want to maybe look at the average magnetization of the time-evolved Hamiltonian over all one local Pauli Z observables. So there's different steps of preparing a target state and estimating the observable. So first of all, there's state preparation. Then you apply your quantum circuit of interest, which could include the state preparation as well. Once you're done, usually you acquire some shots, do post-processing, and then compute the observable value. So on a fault-tolerant quantum processor with error correction and so on, all of these steps should be implemented as noiseless, so then you don't have to worry about that. But on the current devices, there's noise, and the noise depends on the implementation, on the modality, so which type of qubits do you use, and control systems, everything. So each of those noises affects the steps differently. So let's look at state preparation error, right? So typically you say, well, I just want to initialize a state in the zero state, but if you have thermal noise, you may end up in a one state accidentally, right? So sometimes you want to do a resetting a qubit. You just measure it, and you know it's in one or zero, and then you may apply a NOT gate if it's a one, and then you hope to end up in the zero state. But if you misclassify the measurement, then of course you're also not in the zero state. So in general, maybe the noisy state will be some factor of zero and some part ones. Okay. Then, of course, you want to apply a quantum circuit, and in superconducting quantum systems, that means that if you want to apply the individual gates, that amounts to microwave pulses. So in this case, the gates may be miscalibrated, right? The frequencies of the qubits may have shifted or just drifted over time. And there may not be accurate enough control of the pulses, so that can lead to coherent error. So, for example, here's some pulse with an envelope, and maybe what happens is maybe the amplitude is not high enough, so you don't put enough Hamiltonian in there, so you don't really do the rotation you want. You may under rotate, or maybe the pulse length is too short. or too long. And this just leads to inaccurate gate applications, right? At the same time of applying this gate, the pulse, there's other processes going on. Qubits may slowly decohere, so that gives rise to dissipative errors. And for example, a qubit in a state 1 may gradually relax to state 0. In addition, there may be arbitrary two-level systems that are not engineered that way, but that just happen because of minute irregularities. So this also affects the qubits. Then you want to measure the qubits, right? And usually the output of a measurement is a point on this IQ plane. So you get some points, and if you have a 0 state, you may end up with the blue dots, and 1 state you may end up with these red dots. And once you measure them, you want to separate them. So you use some machine learning to find the best plane that separates the two, and then you say on the left is 0, on the right is a 1. But the distributions may not always be so nicely separated. They may be closer together. This is, of course, exaggerated, but you would misclassify a lot, and based on individual points, you can't really say if it was a 0 or a 1. So then the last source of noise, which is not really noise or to do with mitigation, is that we usually measure in the computational basis, so you measure Pauli Z observable. And that means that if you do a single shot, you get a plus or minus 1 observable value. And the expectation value over infinite number of shots then gives you the observable value, if we just disregard all the other noise. But because you can only take a finite number of shots, you have a standard deviation of 1 over square root of n. So that's just the standard deviation in your estimate. And this is statistical uncertainty. So this is not something you can just sort of mitigate. This also applies to fault tolerant settings. So even if your quantum computer is perfect, this will still be a noise source, but we'll mostly ignore it. So the different sources of noise, they lead to inaccurate observable estimates. And error mitigation is one technique that can help you try and improve your accuracy of the observable value. So here's just an overview of a number of techniques. So the first one is probabilistic error cancellation. Here we just have a circuit where we have noisy gates that consist of some noise process plus an ideal gate. I'll explain later how we split this up here. And the goal then is to implement sort of the inverse noise map. So then if you implement that correctly, the orange and pink boxes just cancel, and you get your ideal circuit. The second technique is zero noise extrapolation. So what you do is you have some standard noise level, let's say 1, and you measure observable. Then you're going to actually increase your noise level and say, what do we measure then? And you do this for different levels, and then you just say, let's extrapolate it and evaluate it at zero noise. So that's another technique. And then, of course, there's various forms of readout error mitigation. Yeah. So a fourth one here is error detection using coherent Pauli checks. This is a technique that tries to improve the individual shots, not just the average observable value. So it's a little more difficult to do this on a shot-by-shot basis, because when you average, you have a lot more freedom to do certain operations. Okay, and this is just a review paper that reviews a lot of error mitigation techniques. So if you're interested, that might be a good source of references and pointers. Okay, so let's look at the first part of the lecture then. Noise channels, noisy gates, readout error mitigation, and noise learning. So we can represent the quantum state by some density matrix rho, and you can take a spectral representation with some orthonormal basis phi here. So you can write it as a sum of probabilities times these values. So they sum up to 1. Now all density matrix have unit trace, and you can just look at it. The trace of rho is the trace of this. You just rotate the terms here, so you get the inner product with itself, that is 1. So you just get the sum of the probabilities, which will be 1. Right, so that's unit trace. One fact we'll use throughout the talk is that the trace is linear. So the trace of A plus B is the trace of A plus the trace of B. So density matrices are Hermitian and positive semi-definite, and that's just, you can look at it for yourself. You just apply some state on both sides here. You then take the trace and just work out the details here, and then you get some sum of non-negative values, right? And that will be positive. So that holds for any state or any vector here. So one of the key components in this work is a set of Pauli matrices, right? So it's a basis for 2x2 Hermitian matrices. So this is just the identity matrix, then Pauli X, Pauli Y, and Pauli Z. And you can write any single qubit density matrix, so a 2x2 matrix, as a summation of those 4 components, where this alpha value is a real value. Otherwise, it would lose hermeticity. Okay, so these Pauli operators, usually we just write I, X, Y, and Z, so we don't have to deal with the arbitrary 0, 1, 2, 3. And based on the individual Pauli operators, we can define multi-qubit Pauli operators. So maybe X, I, Y, Z, short for X Kronecker, I Kronecker, Y Kronecker, Z, X. So we can denote the set of all of the Pauli matrices as P of n. So there's 4 to the n minus 1. Well, there's 4 to the n ones. Usually you start labeling at 0, so there's a minus 1 term here. And you usually say that the P0 is identity. Yes, question?
Sorry, in the previous slide, when you said that the trace of the S matrix equals 1, are we assuming that it's a pure state?
No, I don't think so. I think if you take the product of rho squared, that would no longer be satisfied. But for pure states, that would still be 1. Otherwise, it's less than 1. Yeah. Okay. Okay, so let's see, where were we here? Then another important thing is that the trace of A Kronecker B is equal to the trace of A times the trace of B. Right? So now if you look at any of these matrices, the trace is all 0 except for the identity. Right? And so if any of the components in a Pauli is not identity, then that term would have a trace is 0. So the trace of some Pauli is non-zero only if it's the identity. Right? Finally, Pauli operators are self-adjoint, so P dagger is the same as P. You can see this is just all symmetric, and here if you first take the transpose, then you get minus I, and then you take the complex conjugate and you get back to Y. So that holds. And so if you square it, it goes back to the identity. Now, usually I'll just write the dagger anyway, but that's more for the form, but rather it's not really necessary in this case. Okay, so now let's look at some physical noise maps. So a noise map, what you want is it wants to map one state to another state, and that means that your map should be CPTP, so it's completely positive. It maps any PSD matrix to a PSD state, right? And it's also trace preserving. So the trace of one of row prime is the same as row. And that just means that if you apply the map to a state, you get a state. It stays physical. So as an example of a noise channel is a depolarizing noise channel. So if you apply that on a state with some probability 1 minus eta, it does nothing. And with probability eta, you get the maximally mixed state. Right? You can also define a global depolarizing channel, so that acts on the full state on all qubits. In a lot of error situations, you say, well, you have local depolarizing noise, maybe single qubit or 2 qubit, just for simplicity.
Question. So the top of the previous slide, is that a reflection on how nature works, or is that what we know how to do math on?
I'm not entirely sure if that reflects nature, but I think it's reasonable assumptions that it should hold. Yeah. Okay, so the main important noise channel in this talk is a Pauli noise channel. And this has the form as follows. So the noise channel applied to some state rho is just a summation of some pi. This is some probability value. You apply a Pauli I on the state. And so here, what does pi rho pi dagger mean? It's just you applied the gate, let's say. So one way to see this is with probability pi, you apply some Pauli operator to the state, where the probabilities here are non-negative and sum up to 1. So here, as I mentioned, U dagger just means apply the gate. So you can see it more clearly from the spectral representation if you're not used to density matrices. Here you just apply U to the state, and here's just the adjoint of this. Right? So that's your new density matrix. So for the Pauli channel, you could see it as just with some probability, you take a sample and you say, I'm going to apply this Pauli gate to the state at random. So given some noise channel like this, we can define the Pauli fidelity as the fidelity of some Pauli I under the channel is you apply the channel on the Pauli, right? And then you say, well, what is sort of the inner product with the Pauli? What is the component pi within this state? Or how much of this is in the state? That's just by taking the trace. So if lambda is a Pauli channel, you just have to plug in your pi. You have your summation over j, probability p. You apply Pauli p, and then you take this last pi here at the beginning. Right. So that's a lot of terms there, but let's try and simplify this a bit. So one property of Pauli operators is that if you multiply them, then if you switch the order, so pj times pi, and you switch them, that will be plus or minus, right? So that holds for any Pauli. The sign is positive if and only if Pauli I and Pauli j commute. So how do you determine if two Pauli operators commute, right? So we already saw that, I don't think we saw this yet, but if you have a Kronecker product of two terms, just general matrices, that doesn't matter. S1 Kronecker S2, you multiply this by T1 Kronecker T2, then you just take the product of the first two Kronecker, the product of S2 T2, right? So we can apply this to Paulis because multi-qubit Paulis is just the Kronecker product of the individual terms. Per term, we can decide if it commutes or anti-commutes. You get a plus one or a minus one, and then you just multiply these plus or minus ones, right? So the identity term commutes with everything, right? Because identity times some p is p times some identity. That's obvious. Now, each of the x, y, and z terms commutes with itself, and of course with the identity, and all the other ones anti-commute. So x times y is minus y times x. So here you just use this rule then here to multiply the signs. If there's an odd number of negative signs, it's anti-commuting. Your overall sign will be minus 1. Okay, so applying that to this part here, we can write pj times pi is minus 1 to the symplectic inner product, which will be 0 or 1, times pi pj. Right? So this is just a difficult way of writing plus or minus 1, essentially. So we can just expand the channel. So the channel is apply the pj terms here on I, that's the inner part here, and we just add the brackets for the next step, which is we're going to apply this rule here, and we get our sign. Then of course we flip the I and j position, so then you get pj dagger, and that was always the identity, right? So this term just goes away, and that means that you end up with a sum of pj times these signs times the original, right? So it's some fidelity I times pi. So one way to see this is that pi is an eigenvector or an eigen operator of the channel with some eigenvalue fi. Right. Okay, and the fidelity here is given just by this minus 1 to the symplectic inner product times pj. So if you look at this, that each fi is a linear combination of these probabilities, because this will always be the same regardless of the probabilities. So we can write f is equal to some operator, which is the Walsh-Hadamard transformation, on your probability vectors. Right, and the elements of Wij are just these symplectic inner products. Yeah.
Is the symplectic, is that like with the standard like null, like the block matrix 0, 1, minus 1, null? Like,
yeah. So if you write p in terms of its x and z components, then you just flip the terms in the other and then do element-wise multiplication and then sum them up modulo 2. This is just the transformation. On classical computers, you have fast transformations for this, but of course, the size of this matrix will be 2 to the n by 2 to the n, so or maybe even 4 to the n by 4 to the n. So you can only apply it for smaller systems. Yeah.
Isn't pj like for a specific j a number?
Oh, sorry?
Like pj for a specific j is a number, right? So
Yeah, so this would be a number, that's right. This is just...
so what do you mean by linear combination of vector pj?
Well, the capital Pj is the Pauli matrix, or the
Right.
Pauli operator. This is just a scalar probability value.
Yeah, so you'd say each fi is a linear combination of vector pj.
Oh, yeah, well, it's a linear combination of if you've put all of the Pj's in a vector. But that you could write as a linear combination of the terms if you just write out the sum of the matrix vector multiplication. Right? This is just the summation of plus or minus 1s times the terms. Yeah. So this transformation here, this just allows us to switch between Pauli channel fidelities here and the probabilities. Right? If I give you the fidelities of the channel, you apply the inverse Walsh-Hadamard and you get the probabilities and so on. So for example, if we have a channel where you have 0.9 times the original plus some terms here for x, y, and z, then the Walsh-Hadamard for a single qubit Pauli is just this matrix, right? Everything commutes with the identity. terms themselves commute with each other, and all the others, they don't. That's just -1. So let's just multiply this vector here, 0.9, 0.2, 0.5, 0.3, times this matrix, then we get the fidelities. Right? And the fidelity of the identity is always 1, because it's just the summation of the probabilities, which will be 1. So for n-qubit Paulis, the Walsh-Hadamard is just the Kronecker product of this to the power n. So, yeah.
So if it's more than 1 qubit, are you assuming some kind of order, like for this to be the Hadamard transform?
Yeah, and for this one, I mean, if you change the order I, X, Y, Z, then it would be different. So you have to take, let's say, I, X, Y, Z, and then Kronecker that with I, X, Y, Z to get the order. So you get I, X, I, Y, I, Z, and then X, I, X, etc. Yeah. So of course, this is just a matrix representation. As operators, it just has to be consistent. But this is just the way to write it as matrices. Okay. So given any quantum operator, we can define a 4 to the n by 4 to the n matrix M here, where the columns correspond to some input Pauli. So I input some Pauli Pj, I apply the operator, and then I measure how much of Pauli I is in the result, right? What is the component of this in the new state. So this matrix is called the Pauli transfer matrix, and it just says how, if you put in one Pauli, which other Paulis it maps to. And this is a convenient way of writing operators, at least on paper, because they grow quickly, of course. If we have two states, rho and the application of just the operator on rho, and then we vectorize the matrices. So first we express rho as a sum of Paulis because there was a basis for remission matrices, so we can express this. We can do the same for rho prime. And then it turns out that if you look at the Pauli transfer matrix of the operator, then this is just a matrix, this is a vector, and these coefficients are just the matrix vector product of the elements, right? So you just multiply the matrix. And that means that the operator is fully characterized by its Pauli transfer matrix. So one important property is that if you apply two operators, first V and then U, then the Pauli transfer matrix of this combination is just the Pauli transfer matrix of U times the Pauli transfer matrix of V. So that makes life very simple. Okay, so any questions about this?
Actually, I have a question.
Yeah.
So back 2 slides, I think. I understand all the math. I see how you go from the coefficients of the terms of the noise channel. What is there a nice heuristic for understanding what the 3 fidelities, what do those channels actually correspond to after you have made that transformation? Walsh-Hadamard. Not just the X channel, Y channel, Z channel. This is some combination of them, right?
No, I don't quite get the question.
Is there an easy heuristic to understand what the eigenvectors are of the Walsh-Hadamard transformation?
Oh, it's
this Pauli structure.
Yeah, it's not so much the eigenvalues of the Walsh-Hadamard, right? It's the eigenvalues of the channel.
Right. So is there an easy way to understand what the eigenvectors are? Namely, what do those 3 fidelities actually correspond to?
Well, all I can say there is it's just a linear combination of these probabilities. I don't have a bigger intuitive picture about this. Yeah. There may be some underlying geometry. I don't know.
Yeah, I guess that's what it's not that obvious.
Maybe, I don't know. Yeah, let's see, where were we? Yeah, so Pauli channels have a very specific Pauli transfer. Oh yeah, question.
Sorry, on the previous slide. So you have the map from the alpha I primes by applying this matrix, right?
Yeah.
But if you go to the previous slide, don't they have to sum to 1? Or you've done that here, right?
What the alphas don't have to sum up to 1.
Right.
Yeah. I think in the 2 norm there will be 1, if I'm not mistaken. But yeah. Another question?
I just was trying to understand what the Pauli transfer matrix was. So it says that it changes the amount of PI.
Yes.
You did in the operator times PJ, so it almost seems like a sort of a fidelity. I was just wondering what it didn't make sense to understand that.
Yeah. So.
Could you summarize the question?
So the question is if I understand correctly, sort of here you have the p-values, right? And then on this side you have the fidelities and how they correspond, right? Or
I meant more for the Pauli transfer matrix, so the next one.
oh, the next slide. Sorry.
So
Okay. How the fidelities change. That yeah.
just because like it says amount of PI in operator times PJ, so it seems like fidelity to me.
Yes, in a way, yes. So I think it may depend on how you define the fidelity. Usually it's on the same Pauli input, right? So the diagonal elements, there will be the fidelities.
So what would you use the PTM for in general?
Well, it helps to analyze things just in terms of linear algebra much easier. And you can represent certain operators much easier in this manner. But I'll show one example of why this matrix notation helps, or at least for a more intuitive picture. Yeah. So let's look at the Pauli transfer matrix of a Pauli channel, right? So if we have some Pauli I times Pauli j, then when the terms are the same, it adds up to the identity, right? Otherwise, it's some Pauli q that is not the identity with some phase plus or minus 1 plus or minus I, right? I think it's just plus or minus I in this case. But so we already saw that if you put a Pauli in a Pauli channel, then you get some fidelity of the Pauli, right? Now, if you look at the full matrix here, we just need to evaluate this. Now, if I is j, then we saw that this lambda pj turns into some fidelity times pj, right? And if this first pi is also equal to pj, because I is equal to j, then you get the identity term, and the trace of this is 1. Well, I mean, up to this scaling factor. But so then you get the fidelity. Otherwise, this pi pj will be some non-identity Pauli, and we already saw that if you take the trace of any non-identity Pauli is 0, so this is 0. So that means that the Pauli transfer matrix of a Pauli channel is just the diagonal matrix with the fidelities on the diagonal. Yeah. Good. So also, just because of the linear algebra here, you can see that if you apply 2 Pauli channels, the order doesn't matter because, well, if you multiply 2 diagonal matrices, it's just, yeah, the order doesn't matter, so they commute. And that will be much harder to show if you just work out the full Pauli channels. So that's not as obvious. Okay, so just a brief recap up to now. We have Pauli channels, just the sum of applying a Pauli with certain probability. You then define that a channel fidelity for that particular Pauli as such. And we can switch between this representation, the probabilities, and the fidelities by means of the Walsh-Hadamard transform. So Walsh-Hadamard and probabilities, fidelities, and the inverse Walsh-Hadamard and fidelities gives you the probabilities. And the inverse Walsh-Hadamard is just 1 over 4 to the n times the Walsh-Hadamard, where W is over n qubits in this case. Okay, and the Pauli transfer matrix is diagonal. Yeah, Chris.
I have a sort of just an understanding check. So we start with a 2 to the n by 2 to the n matrix, which has 4 to the n entries, and then we create this Pauli transformation matrix, which is a diagonal of 4 to the n elements.
Yes.
And they're kind of the same thing in a way. We can go back and forth between them.
Yes.
That's okay. Thank you.
Yeah, that's right. But sometimes one representation is much more convenient than the other.
I imagine.
So it's like a Fourier transformation. One is you're in frequency space, other one in normal space, if you like. Yeah, question.
I'm sorry, a little confused on the statement that the ordering of Pauli channels don't really matter, because if I have a Pauli channel that just applies X all the time, and another one that applies what, like Z all the time?
Yes.
And since they're anti-commute, shouldn't the order kind of matters in a circuit?
Well, I think in both cases, the thing that happens there is you apply X here and you apply X here, and then you do the Pauli channel around it, which would mean you have a Z here and you have a Z on the other side. Those you can flip. Then each side might have a minus. So you have minus on the left and a minus on the right. So those will still cancel. Yeah. Okay, so Pauli channels turn out to be very convenient to work with. Well, first of all, you don't have 4 to the n by 4 to the n parameters. You just have 4 to the n, which is still exponential, but a lot smaller. But of course, not every noise channel is a Pauli channel. So what can you do, right? We want to ideally work with Pauli channels. So one concept is called Pauli twirling. So given some noise channel, you just define the twirled noise channel as the average over all Pauli's I of you first apply the Pauli on the state, then apply the noise channel, and then you apply the conjugate, which is just the same. So you apply the Pauli again. And it's just the expectation value of this. So as a full operator. So what does this transformation do? Okay, so let's just look at the Pauli transfer matrix of the twirl channel. So because the Pauli transfer matrix of these operations is just the product, first we apply this calligraphic pi, which is just defined as p on either side. Then we apply the noise channel and we apply the dagger. So this is where the graphical representation of the matrices comes in handy. So the Pauli transfer matrix with respect to some, you apply p on either side, is just a column of this Walsh-Hadamard. It's just plus or minus 1 elements on the diagonal. Then we have something, I'm not sure if it's supposed to be, no, it's not symmetric necessarily, but of your channel. And then you again apply this diagonal. Now, if we just ignore the summation for now, what a single element would do is you would multiply each row here with some value here, right? So you sort of apply your weights on the rows, and here you apply the weights on the columns, right? And you can just write this out as the outer product of Wi transpose, element-wise multiplication with your Pauli your transfer matrix of the noise channel. Okay. Now, the diagonal elements here is the sign will be the same because the location in the vectors is the same. So that will always be 1. And it turns out that if you take the average over all of these i's, that with 50% of the times this is a +1, 50% it's a -1, so they cancel out. So what you end up with is just an identity matrix. Okay, and now we're doing element-wise multiplication. So we just end up with a diagonal matrix, and this was a Pauli channel. So by applying this twirling, you can map any operator or channel to a Pauli channel. So that's very convenient. Okay, so now we take a summation here over 4 to the power n elements, right? Are they useful in practice, and can they be implemented? And yes, it's very useful, and we can implement them, not necessarily exactly, but at least in expectation. So if you consider the evaluation of some observable expectation value of this channel, right, then we use linearity of the trace. So the trace of a sum is a sum of traces. So we can write this as the trace of all of these individual terms here. And that means we can write it as the sum over all of the Pauli twirl elements. You apply one, you evaluate the operator. This is something you can obviously do because you just have a circuit with and without the PI here. You measure it and then you can evaluate everything. So if n is small, you could actually generate all 4 to the n circuits and on average implement this Pauli twirl. Right? But if n is larger, what you just do is you just randomly sample circuit instances. You choose your PJ at random, uniformly at random, and then in expectation you get the correct observable value. Right? So you might choose XZ and measure it. You might take IY, etc. Right? So any questions up to this point? Yeah.
Okay, I have one question about the CPTP assumption of noisy channel.
Okay.
I think it corresponding to the dynamics of open quantum system under the Bohr-Markov assumption, which
Okay.
could be a strong assumption. Is it possible to, I think a more general assumption like a CP evolution could be useful to describe a more general noisy channel.
Okay.
So, like, do you have any comments about it? Is it recommended, or you think like a Markovian assumption noisy channel is good enough to describe most noises in the quantum?
Usually what we do is we assume Markovianity.
I mean, okay.
But yeah, and in terms of which channels, we also just assume it's CPT. I don't know about the details of if you relax these conditions or if you make them stronger. Yeah, this.
Another question I have is about the assumption of the noisy channel, especially the interlacing structure between the noisy channel and the recovery operator and the ideal gate.
Okay.
So in this assumption, it seems like there will be a Trotter-like error due to this interlacing structure.
I will get to that a little later.
Oh, okay.
Yeah.
Thank you.
Yeah, question.
So for this specific experiment, what are we trying to do here?
So this is, so remember if we want to twirl, let's switch it off. Yeah, so for a twirl, let's see, go back a little, oops. So for a twirl, what we want to do is a summation over any PI here and PI on this side. So that this means before the noise channel, apply the noise channel, after the noise channel, right? So this is just a summation of everything. So what we're trying to do here is we just have one instance PI. We construct a circuit corresponding to that. You apply your PI, lambda PI, right? And then you would measure some observable. So if you would do this for all of the PI terms, you get the observable under the Pauli twirled noise channel.
So like from the left, there's like some unknown input row.
That will just be rho, yes.
And then you pass this noise channel, and we want to measure the observable here. That's the experiment.
Yes, but we want to measure the observable under the Pauli twirled noise channel.
Okay.
So after we do this, we can just say, let's assume that the noise channel is a Pauli noise channel.
But like, okay, so in this specific experiment,
Yes.
if you just want to measure, row after the channel, you want to measure the observable, you can directly measure them, right? You don't need to use any.
Yes, but then you would just apply your original noise channel, right? Now, I'm not
Right.
saying that you can necessarily apply a noise channel explicitly, right? Because that would be silly to just randomly apply a noise channel. But what we want to do is that on average, we shape this noise channel into a Pauli channel, because then we can do more operations with it. Question?
So this is like a kind of simplifying the channel, like you said, to a Pauli.
Yes.
I assume that it is not a reversible operation where you cannot map it back to the original channel.
No, because you have the element-wise product there, right? So yeah.
So what I'm wondering is like, is there any metric to quantify how close the Pauli channel is to the original channel?
Well, the diagonal elements they survive, right? So that's left unchanged. In terms of a partial Pauli, now if you take outer products of vectors of plus or minus ones, and you start averaging them over a finite number of elements, then you would see the magnitude of the off-diagonal elements to slowly go towards zero. So in that sense, it gradually goes to the Pauli noise channel.
Right, but there would be some channels where you have like, the off-diagonal elements be more significant. Like I would assume it wouldn't work, like the polytoning wouldn't work as well as for like those channels where the off-diagonal elements are.
No, it might take a bit more time to on average get rid of those. That's right. Yeah. Oh, yeah.
So this summation, if I understand correctly, is n to the 4 to the n, right?
Yes.
It's very long.
Yes.
So you do some random sampling.
Yeah.
It could be a very small fraction of that. Do you have some techniques to get like a principal components? The most.
No, I
important?
think what we do is we just randomly sample them. We just don't assume anything about what was mentioned about the off-diagonal terms. If you could try and sort of engineer it, I guess, for very specific, but otherwise you just randomly sample it, and thus choose the concentration of measure that it concentrates around the expectation value.
But out of a 4 to the n, in a pairs that you are doing a very small fraction.
It is a very small fraction, but it still seems to work well in practice. But yeah, it's right. It's just a very small probability.
Okay.
Yeah.
So Pauli drilling seems to convert any noise channel into a Pauli channel.
Yes.
But I'm wondering, can it convert any arbitrary noise channel into a Pauli channel, or are there any conditions? I guess it's really.
No, I don't think so. It really takes any. I think even if you have a coherent rotation, it will still turn it into Pauli. So yes, not what you want to do, I think, but yeah.
So I just wanted to make sure, is there an assumption that the noise channel lambda maps the identity to identity operator? So it's a unitary noise channel?
Yes, I think so. Yes.
Does this twirling still map to a diagonal like TTM in the non-unitary noise case?
This I don't know. Maybe you have to check it. Yeah. Thanks. Okay, so let's move on to readout error mitigation then. So as I mentioned in the introduction, right, the measurements of the quantum circuits are usually given as some binary outcome string, just 1, 0, 1, etc. If you measure several, along with the shot count. So you just do a lot of runs. You get bit strings and you just put them all together. You say how many times did you see each shot? So from these you can estimate observable expectation values, and I'll show later how this is done. But the measurement process is prone to errors. That's one thing, and then of course the classification may not be perfect. Once you have a point here on this line, on this side of the line, you just say it's a 0, even though it may have been a 1. So that's just a misclassification. Now, if I just give you a point here, then based on this information, you cannot say if it was a 0 or a 1. I mean, there's some red points here, and they might overlap exactly, so you can't differentiate. So that means that you cannot really correct individual shots and say, oh well, this was something else. Although you could use some repetition code and try to do that. What we can do is can try to improve the distribution of the bit strings or the observable values, right? So what would be the ideal measurement, right? So if we have a number of qubits and you have zeros and 1, then you can make it into a binary vector and just assign it some integer. So the probability of measuring this k is just this expression here, or the trace with the outer product of the two. But this, if you look at it, it just means there's a 1 in a vector of 2 to the n at location k. If you multiply on both sides, you just extract the kth element of the diagonal of row, right? So the diagonal elements of row, which sum up to 1, as we saw earlier, that will give you the distribution of measuring these computational basis states, right? So let's just look at a single qubit case, right? So let's assume that errors occur independently per qubit, and they take the form of a bit flip. So there's no leakage or anything, just 0s might map to 1 and 1 might map to 0. So what we can do is we can write some confusion matrix, right? What is the probability of measuring 0 when it was indeed a 0, or measure 0 as a 1? There will be one column, and because if the state was 0, you always measure either 0 or 1, this will sum up to 1, and likewise for measuring a 1 state as either a 0 or 1, right? So if P is the probability distribution of measuring 0s and 1, then after this transformation, you would measure according to A times P, right? So you just map it. So this matrix is left stochastic, it has no negative entries, and the columns sum up to 1. So in the multi-qubit setting, one simple solution is to say, well, let's just each qubit independently have its own matrix, and you just take a Kronecker product of those matrices. So that's also easy to represent. Now, if you have an ideal distribution of 30% zeros and 70% ones, and the readout error on 0 state would be 2%, and the readout error on ones would be 4%, then you just multiply it, and you see that there's some shift in the probability of measuring a 0 and a 1. So then the obvious thing to say is, well, why don't we just immediately apply the inverse A matrix, right? And you could do this. You can just mathematically do it and say, I'm just going to do it. But it's no longer left stochastic, and it can have negative entries. So that means that if your distribution is empirical, you just sample a bunch of times, then you can end up with negative probabilities. Right? Maybe if you calculate observable values, you just close your eyes and just still calculate it. But what you can also do is you can say, well, find the best probability distribution that when you apply A to it, it's as close to your measured probabilities as possible. So that's something you can do. Of course, if A is a Kronecker product of a large number of qubits, this will be expensive. Okay, so how do we determine or estimate A? So first of all, of course, you can just prepare a 0 and measure it, and then I get a bunch of zeros and a bunch of ones, and then I know what the first column should be, and then the same for the second column. So let's say you take 1,000 shots each, and we measure 932 zero values from 0 and 957 from 1, then you just divide by 1,000 and you get this matrix. Right? This is what you will then say, this is the confusion matrix for this readout. So this is just two probabilities here, and usually measuring 1 is harder than measuring 0 because it might decay towards 0 as you measure it. So this is not the symmetric matrix in general, but you can symmetrize it by applying twirling on the readout. So just like we apply Pauli's around the channel, you can also apply certain gates before measurements. Yes, question?
So when you get these numbers, when you initialize to 0 or 1, there's also a chance to error. Right?
Yes, state preparation is a problem.
So then how do you know like what these values are?
You wouldn't exactly know for just the measurement. This is a problem. It's hard to separate the state preparations from the measurement errors.
Okay.
So what you then do is just you either try to do this, but I'm not sure if it's completely possible to separate them, or you just say, okay, let's just work with this. Best
So
effort.
we assume like state prep is much better than measurement?
Yeah.
Okay.
Yeah. Okay, so if we want to symmetrize this, we can apply readout twirling. And how does that work? Well, we can just apply a X gate before readout that will change zeros in ones, ones in zeros. Then we measure it, and if we applied it, we just classically flip the bit as well, right? So then there's two paths to measure a 0. Either you directly measure it, or you first go to 1, measure 1, and have the readout error of measuring a 1, and then go back to a 0. And that will average the term, so it'll make it symmetric. Of course, if you do this empirically, there will still be some residual, so you can just enforce symmetry in that case. You just symmetrize the matrix. And as you mentioned, right, so the state preparation error inhibit learning A exactly. It will be part of this matrix. Okay, so if you just mitigate using these confusion matrices, it's conceptually simple. It does require some assumption that if you measure a bunch of qubits, they don't affect each other. It's just individual. And just forming this entire matrix explicitly or trying to work with it on a large vector of all the possible probabilities, that's not very scalable, right? Because the vector of measurements is 2 to the power n, that's a long vector, and then you need to maybe do some optimization problem. That doesn't scale well. There are some more scalable approaches here. So I just point to the references here without going into detail of those. But let's look at one readout error mitigation method for observable values. So if you look at the density matrix rho, we saw that the elements on the diagonal give you the measurement probabilities in the computational basis, right? And those diagonal elements, though they can be expressed as a sum of Pauli Z components, because this is the identity, this is Pauli Z, this is the only way you can get diagonal elements, by combining these two matrices, right? So they just give you the measurement probability, so that suggests that you can measure Pauli Z observables based on the measurements, right? So the probability of measuring Z is just this trace here. And likewise, the probability of measuring a 1 is given by this expression, so here. Now, if you explicitly write out this operation here, this is just a 1 in the upper left corner. The 1, 1 is just the 1 in the lower left corner. So the Z matrix is just this expression minus this one, right? So there. So that means that if you take the trace of some z with a row, then you just expand it, and then we use linearity of the trace again, and what you end up is the probability of measuring 0 minus the probability of measuring a 1. Right? So that's how you can get the Pauli z observable value. And likewise, if you do the trace of the identity, is you get this term plus this term, so it's the probability of measuring a 0 plus the probability of measuring a 1, which is always 1 because you measure something. So that's for a single qubit. And you can do the same as in more qubits. But let's first write it like this. So the state can be written as a half, that's just normalization of some alpha 0 times identity plus alpha 1 times z plus off diagonal terms. Let's just ignore them. All right? And so these alphas can be written as the sum of these probabilities, probability of measuring 0, probability of measuring 1, multiplied by Hadamard matrix. Right? And this extends to multi-qubit states. So if you have all of the diagonal elements and you pre-multiply it with the Hadamard Kronecker to the power n, then you get all your Pauli z observable values. So this means that you can switch again between the computational basis measurements and the Pauli z observable values, just using the Hadamard transformation in this case. So again, this is sort of a Fourier representation of the same. Okay, so if you measure an observable expectation value, right, you take a whole bunch of shots and you calculate the contribution of each individual Pauli z observable given the shots, right? So if I have a single shot that has bits 1 to bits n, and some Pauli terms that are either I or z because we want to measure Pauli z, then you can see that if the bit is 0, you pretty much measure the left upper diagonal element of the operator, which is always 1, so that will be a +1. The only time you have a -1 contribution if your bit is 1 and your corresponding Pauli term is z. Right? So if your measurement was 1, 0, 1, 0 and your observable is I, z, z, I, then I with the measured 1 is a 1, z with the measured 0 is just a 1 as well, z with the sort of bottom right element, that's a -1, and identity with anything was 1. So you then multiply them all together, right? And then you get a -1 outcome. That's for that shot, the sort of value contribution is -1, and you take a lot of shots to get the expectation value of your Pauli z observable. Now, given a bunch of shots, that also means you can just select any number of Pauli z observables you want to measure based on it. There will be correlated errors, of course, in statistics, but otherwise you can evaluate the observable expectation value for all of the 2 to the n Pauli z observables. So now, what if we want to measure something else in the Pauli z observable, right? Or maybe just anything else. So if we want to do other Pauli observables, we can just insert basis change gates before measuring. So if you apply a Hadamard gate, it will change x to z and vice versa. So if you want to measure x, you first apply Hadamard, it will be a z, and we can measure z's, right? And likewise, I think square root of x dagger changes y's to z's. So that way, if you want to measure any Pauli string, you change the basis and just measure it as Pauli z's. For more general observables, you can first decompose it into its Pauli terms, and then measure each independent one and use linearity of the trace to again combine the expectation values of all of the components. So one final method for readout error mitigation for observables is the twirled readout extinction method, T-Rex, in this paper here. This is a mitigation of readout errors in observable estimation. So it's based on twirling of the readout and scaling of the Pauli Z observables. And it kind of assumes that there's no state preparation error. If there's an error in state preparation, it's very clear how it shows up, but not very clear how you would get rid of it. But let's just look at the process, right? So we can just vectorize our density matrix rho in terms of Pauli terms. And let's just write down the coefficients. First, all of the Pauli Z terms in alphabetic order, and then the rest. You don't really care about the rest because they don't contribute to the diagonal, so you can ignore them, at least on paper, for the probability of measuring stuff. So this alpha is some Hadamard times the probabilities, right? So the ideal measurement probabilities are H inverse times alpha plus 0 times the rest. We just ignore them. So now we have access to the probabilities based on the Pauli components of our density matrix. Then we had some arbitrary multi-qubit confusion matrix A, which we don't need to know. But applying this would get you sort of the actual measurement distribution, right? After readout errors. So that's P hat here. And then we convert these noisy probabilities back to the Pauli Z component by just applying the Hadamard, because we had the Hadamard and the coefficients relation here, right? So we just apply the inverse Hadamard. So that means that alpha hat is H inverse times rho, if you like, or the Pauli coefficients of the density matrix as a vector. Okay, so that's the model. But now we can twirl over this I and X, or the entire Pauli group. It's essentially the same. So each twirl element results in a diagonal plus or minus 1 Pauli transfer matrix on the state, right? So here this matrix DI just applies on the alpha components, and then there's some other diagonal matrix that applies to 0, but just ignore that here. So because twirling applies to both sides, you just multiply both. And just like before, this amounts to an outer product of plus or minus 1 vectors. So element-wise multiplication. And then after twirling, you can see that this term again goes to the identity. And that means that you get an identity times something. That will be a diagonal matrix times rho. So the alphas, the Pauli Z components you measure after twirling, is just some diagonal matrix times the actual ones. So that means that each Pauli Z observable after this procedure is just scaled by a single readout fidelity. There's no correlations anymore between the measurements, etc. It's simplified a lot. Yes, question.
Suppression. So I was thinking of this earlier. So on paper, it looks like you only really need to twirl over I and X. You don't need the others. However, in practice, you always need to twirl over the whole Pauli.
I don't. I think we just do X. But if you would apply the other terms as well, you would also zero out the part that is supposed to be 0 but may not be 0. Yeah. I think it doesn't hurt to do it. Yeah.
Normally you would just include them just in case. There's always a small little correction, right? Yeah. Okay.
And of course, afterward, if you apply a Pauli y before, then you would still have to do an x after, not a y, because yeah.
Okay, just one more question.
Yeah, sure.
So here on the previous slide, you took advantage of using the Pauli transformation matrix. Or maybe the previous, okay. Would the calculations be terrible if you were using a more direct representation of the unitary rather than the Pauli transformation?
I'm not sure. Yeah.
Well, at least everything fits into one slide here, but it's like, you said this thing about sometimes it's convenient to have the Pauli transformation. Is this a good example of that this is
Yes, I think so. I think so, because this moving from just diagonals on either side to outer products of signs, and that will turn into an identity matrix. If you write this as a summation of a summation of a summation, it gets a little hairy. Yeah, sure. Yeah. Yeah. So there's now a vector of unknown, let's say, measurement fidelities, right? And if you know them, then if you measure your Pauli Z, you can just divide out this fidelity and get your original A. And so how do you measure the fidelities? Now suppose that you start in a zero state, and this is where you have to assume that it's ideal state preparation. Then you can write this as the summation of I plus Z over 2, right? And in general, any multi-qubit zero state is just the summation of all of the Pauli Z terms, and I think the connection to error correction there is these are all the stabilizers, just as to sum them up to get your state. So if you prepare the state and then followed by the twirled readout, right? Then you get exactly your measurement fidelity, right? So it's just you prepare zero and you start measuring, and that's how you estimate. You get some shots, and given the shots for a particular Pauli Z, you can then evaluate the measurement fidelity. So you don't have to do all of them. You can just say, I'm just interested in measuring this subset of Pauli Z's. You just calculate the fidelities for those guys and just normalize. So this is of course a scalable method, and you don't need to know the A matrix at all. Of course, you do need to have good state preparation. So if you do have state preparation errors, right, then what you actually measure as your twirled observable value, or I think this should be yeah. You measure the product of the state preparation times the measurement fidelity, and this is hard to separate. Sometimes you may want to try and measure the state preparation error. Often you can just assume it's 1. Right? There are some caveats to that. So that's that. So how are we doing? So we discussed some sources of noise, the need for error mitigation, and presented some high-level overview of error mitigation algorithms. Some of the basic concepts are the Pauli transfer matrices, Pauli channels and twirling, and the mapping between Pauli channel probabilities and the fidelities with the Walsh-Hadamard transformation. So for the readout error mitigation, we had the confusion matrices. This is the A matrix, the twirled readout error mitigation, and the mapping between the measurement probabilities in the computational basis and the Pauli observable values using the Hadamard transformation. So I think we do still have a third part. So I probably can get started with this, and then we'll stop somewhere. That works. So now we can get into the question of how do you separate the noise from the gate, right? That was asked earlier. So let's assume we have some noisy gate. What we want to do is want to split it into some noise term, let's say before the gate, and then the ideal gate. And then what we will do later is we want to twirl this arbitrary noise channel into a Pauli channel. So the first step is to split the noisy gates into the channel and the ideal gates. We shape the noise. We'll then try to obtain the Pauli fidelities of this noise channel, and then look at a scalable noise model for this type of systems in our processors, along with some learning protocol. So splitting the noise is actually purely mathematical. So here we have this U tilde, and we can just write it as UU dagger, which is the ideal gate, times some U tilde, right? And we can then just group the terms by U and this term, and this is our ideal gate, and this is just the noise channel, just the noise map, right? So we then just say this noise map is just U dagger U tilde. Okay, so the next step, what we then want to do is we want to shape this noise into a Pauli channel, right? So we want to apply gates before and after, and we want to do this for all of the Pauli terms. So we just have different instances here. But there's one difficulty, and that is that we have our ideal gate here, right? And inserting those gates here is actually done right in the middle of our gate, right? So how do we do this? We just have access to a noisy gate, and we still want to sort of cram in some gates in the middle of this noisy gate. So how do we do that? So this is where we restrict ourselves to Clifford operators, right? So Clifford operators are just a group of unitary operators that map Paulis to Paulis, right? So if you apply a Clifford operator to some Pauli, you get some other, or the same Pauli. If you look at the Pauli transfer matrix of a Clifford operator, it's a signed permutation matrix. So each one Pauli is mapped to some Pauli with a sign potential. Right? Not every signed permutation matrix will be the Pauli transfer matrix of a Clifford operator, but every Pauli transfer matrix of a Clifford operator will be a signed permutation matrix. So there's many useful properties. One of the properties is that if you apply a Clifford to a product of two Paulis, then of course you can just insert an identity here, and that means you have the product of the Clifford applied to each individual term. And using that, you can show that it preserves commutativity. So if Pauli's P and Q commute, so that means PQ minus QP is 0, that happens if and only if your P prime and Q prime also commute. So any two Pauli, the commutativity under the Clifford operators just is preserved. You can implement Clifford operators with Clifford circuits, and those can be generated with just Hadamard phase and CNOT gates. Right? So you can, in principle, implement any Clifford operator with just these three gates. And you can do so actually in polynomial time. So that's the circuits are quite efficient. Now you may have seen this Clifford plus T is a universal gate set. So if you have all of those gates plus you also allow usage of T, then you can at least approximate any unitary up to desired precision. Okay, so now let's look at how we implement a twirl of noise in the context of a Clifford gate, right? So we actually want to twirl before the gate in this case. So we may just want to insert XZ prior to the gate. So what we now do is we first have the Pauli and then the Clifford we can just insert identity here again, right? And then we just replace the brackets here, so we have C, P, C dagger times C. Now, this is just a conjugation of a Pauli with a Clifford. So you apply a Clifford to the Pauli, and you get some other Pauli, Q, let's say. And that means that, well, here we have a Pauli P preceded first and then the Clifford operator, but here we have a Clifford operator and then a Pauli, right? So we can easily conjugate any Pauli with a Clifford operator to get Q. This is efficiently done classically. And in case of a CZ, we just get the XI. So what happens is that this allows us to just take this Pauli here and just move it to the other side. It won't be the same Pauli anymore, necessarily, but you can implement this. You just apply an XI gate here. This is now just our noisy gate, right? And that's how we can do twirling in the context of gates. So that means that we can then really say we have a Pauli noise channel and our ideal Clifford gate. Now, again, this Pauli Q may have a different sign, just let's say a phase factor here, but because you apply with the conjugate as well, those two terms will just cancel. Now, just as a detour, so Clifford operators you can easily simulate, but non-Clifford is hard. And why? If you look at the Pauli transfer matrix of some Z rotation, this is what the Pauli transfer matrix will look like. So you get a cosine sine term here. So if you apply this to a Pauli X, you get some cosine terms X and a sine terms times Y. So it splits up. And this splitting, if you do it multiple times, it will just exponentially increase the number of terms. So that will be very hard to keep track of. So that is why it's hard to simulate non-Clifford circuits. And of course, if you have a non-Clifford 2-qubit gates, it may be even worse. In general, this could be pretty much a dense matrix, except for the identity here.
Wasn't this PTM matrix supposed to be diagonal?
That's just for Pauli channels.
Oh, that's what.
Yes, yeah. So let's say if you apply a Hadamard, then it would leave the Y unchanged. So this would be maybe plus or minus 1, but X and Z would be flipped.
This is the marginal office.
Yeah.
So for Clifford, it should be like a permutation matrix? Or?
Yes, sign permutation.
Okay.
Yeah. Okay, so we can now push the Pauli operators through the Clifford gates, and this allows us to twirl the noise in the context of the Clifford gates. And that's why without loss of generality, we'll just assume that it has already been twirled. Now, of course, in practice, you still need to do it, but just for simplicity, we'll just say that this is now a Pauli channel. So the next two things are then to measure the Pauli fidelities, and I think the scalable noise model will introduce a little later. So maybe I'll try and wrap up the third part. Okay, so here we just take a look at the zero state, right? We could write this as a sum of Pauli I plus Pauli Z, right? Or if you have multi-qubits, just a summation of all of the Pauli Z terms. Now, if you apply a Clifford operator, each of those will map to some other Pauli term, but they never mix. So they don't cancel, they don't do any weird stuff. So what that means is that you can take an individual component of your state and see how it maps through the circuit. And then at the end, you can just sum them up again because there were no cancellations or anything. Right? So if we start with the ZI component of the 2-qubit zero, which has II plus IZ plus ZI plus ZZ, let's just follow one of them. If you push it through the Hadamard or apply the Hadamard, you get an X term. So now we have a Pauli XI. Here we have a noise channel, so this is how you can can simulate this, right? You have your noise channel, and the input Pauli was xi. So that will multiply this by some diagonal matrix or an element corresponding to the xi, and it will also output your xi. So it incurs some fidelity xi. Then we have a CZ gate, and that maps xi to xz. Right? This is just which Pauli maps to which one, and so on. I omitted signs here. So that maps xi to xz. Then we apply the phase gates, that maps it to y. The Hadamard maps z back to x. Then we again have some noise channel, let's say, that just incurs the fidelity of yx. And then we have a CZ which actually changes it to minus xy. Okay, so the circuit maps zi to minus fx times fyx times this Pauli. This is how you can sort of propagate an individual Pauli through the circuit. And then, of course, you can plug in numbers. And if you don't want to deal with just Pauli Z terms, you want to propagate an arbitrary Pauli, you just have to change the basis. So you map all the Z's to, let's say, X and on the first qubit, and the second qubit, you map maybe Z to something else. So that's how you can start with any Pauli at the beginning, move it to the end, and then get some scalar value times the outcome Pauli. Right? And this will be the basis of learning the fidelities of these noise channels. Right? So the basic learning protocol, for example, is you start with Zi, you don't change the basis here, so just apply identity gates or you just don't do anything. You get your Zi, you have a noise channel, you have a fidelity. Zi is invariant under CZ, so it just maps to Zi. So that means that if you would measure this fidelity, modulo state preparation error and measurement error, you would exactly measure the fidelity of this channel for the Zi. Sometimes the terms change, so maybe we want to measure xz, so we first apply a Hadamard basis change, we get xz, we apply the noise channel, get the fidelity, apply the CZ, because this was the noisy CZ gate, right? A combination of noise with the gate. And then we have to measure Zi. So we prepare ZZ and measure Zi. So in this way, it allows us to measure all of the 15 non-trivial channel fidelities, right? And that's all we need to know for this full Pauli channel. These fidelities will be affected by the state preparation and measurement error, right? So in the T-Rex protocol, what we can actually measure is the state preparation of a Pauli times the measurement fidelity of that same Pauli. So in the first case, we would actually measure this term times the fidelity of Zi. But then we can divide by this by just running the empty circuit and measuring the same. So we can get rid of it. But this is not the case if your initial state differs from the final one. Because then we either know the state preparation ZZ times the measurement of ZZ, or the state preparation ZI times the measurement. So we can sort of get rid of one of the two parts, but the other will be some ratio. So that's where you just say, well, okay, if the state preparation fidelity is 1, then we're good.
What's included in the empty circuit?
Just state preparation and readout for.
Not the wait time, with the wait times?
No, this is
straight up.
You might be able to do something there, but yes, it's you just prepare 0, ideally hope perfectly, and then you just measure when you're in a 12 sense. Okay, so then if we're given these noise channels, right? If you have a self-adjoint gates like the CZ, where you, if you square it, you just get the identity, then you always obtain a product of two Pauli fidelities. They may be the same, right? So you start with P1, P2, you move it through. You first have the fidelity of this, then you push it through your CZ gate. You get some Q1, Q2. apply the noise to that, then you get your f of this q, and then you end up with the beginning again. If you repeat this k times, then you just get the power of this to the power k, right? So you do this for different depths, maybe with basis changes if you want. You measure the fidelities to the power k, and you just fit an exponential curve to it. So this will always have one state preparation and measurement or spam error term in front of it, and the decay rate beta will just be the product of fp and fq. The state preparation and measurement there is captured by this alpha. So that's how you measure it. Some papers how to do. So this is just the fidelity as you increase the number of repeats. You fit some exponential curve, least squares fitting. You get your values, and then you just say, okay, that this is just the pairwise product of the channel fidelities. So we can only twirl the noise in the context of Clifford circuits. Otherwise, it becomes a difficulty. There's some work on it, but it's not as nice as for Clifford gates. We can trace out the fidelity or work out the fidelity of a Pauli trajectory as you propagate the Pauli through the circuit. And you can get spam-free estimates of the fidelity pair for self-adjoint gates. But that's just the state preparation and measurement error-free estimate of the product of the two, not of the individual one necessarily. So one question is then, if you can learn the product of these fidelities, can you learn all of the individual fidelities? And unfortunately, the answer to that is no, you cannot actually. And that's a result here in this nice paper here. You cannot learn them in a spam-free manner. And it turns out that you cannot, for all of the Paulis that change the support. So here, there's a support, it's on the first qubit. Here's on the second, and here are all the Paulis with support from both qubits, right? If you change if you apply the circuit here once, you go to a weight 2 observable here. So this is not spam-free because the weight of the initial state and the final state change. So you cannot measure those fidelities individually. If you just measure the product, right? I can divide this by alpha. I can multiply this by alpha. Based on the product, you wouldn't know. For all of those terms that stay in the same fidelity, so maybe a YY and XX, they map to something with the same support. From YY, you can apply single qubit gates to go back to XX. So then you can make cycles of the same fidelity and just learn it this way. So just as to be practical, because we cannot learn all of the individual fidelities, what we just say is, well, the fidelities of xi and xz for this gate, the sort of the pair of the fidelities, they will have the same fidelity. That's just an assumption, because otherwise you get stuck. And this happens to be not a crazy assumption actually. So this way you can just measure everything. So I think that was the end of the first part.